Okay, so we looked at Laplacian, at the intuition behind why we call it a Laplacian, and some properties of Laplacian. So there are different variants of Laplacian. Usually there are normalized variants, and the idea is that if we use Laplacian as an operator, its diagonal terms for the nodes that have too many connections, high degree, it is going to be a higher value. So this operator usually gives results that are, biased toward that node. So one idea is to normalize this. And the idea of normalization, there are two types of normalization that we have. One is symmetric normalization. The other one is random walk normalization. And you will see that each of these will basically show up in different applications that we will see later. So we said that a Laplacian for a connected graph has an eigenvalue which is equal to 0. We can also say that if we have a disconnected graph, the number of 0 eigenvalues is the number of the partitions we have. So, or basically number of components that we have. So for instance, we looked at this in our second session in the first week, and we said that if you have a graph that is disconnected, means that there's no path between this set of nodes to these 5 nodes. So it has 2 components. We can write the adjacency matrix in block diagonal formation, where each block is representing the corresponding adjacency matrix for one of these components. And since the matrix, basically the degree matrix, is a diagonal matrix, if we write our Laplacian as D minus A, our Laplacian matrix is going to be block diagonal as well. And we can show that if we have a block diagonal matrix, we have eigenvalues 0 corresponding to each basically one of these. So the total Laplacian matrix will also have 0 eigenvalues to the number of the connected blocks, basically connected components. For example, here 2. And the corresponding eigenvector will have 1s for basically this block and 0s for everything else. And for this, the corresponding eigenvector will have 0s here and for 1s at the end. So, and we can verify that easily. We can say that each row of, and I'm just showing adjacency matrix here. Let's say that this is Laplacian. And we know that if we sum over all the elements of the Laplacian, it is going to be 0 for each component, right? So if I multiply a vector that has 1s for basically 5 1s and 4 0s, it is going to sum to 0 for all the elements here. And also for all the elements here, because these are going to be 0 and these are going to be 1s. So again, 0s. And you can verify the same thing if we have a vector that has 5 0s at first and 4 1s at the end. So we can essentially use the multiplicity of 0 eigenvalue to find how many components we have in our graph. So that's kind of, clustering, right? We're partitioning our graphs using this method into its basically components. But that's a trivial, right? It is trivial because we already, if it's small, we can see that these are disconnected, right? But we can still use the idea and reformulate the clustering problem using the Laplacian matrix. So, and we call that spectral partitioning. Spectral means that it is related to eigendecomposition of the Laplacian. So let's look back at the cut size that we had, right? We have R, and it was equal to sum over all the basically 2 sums over all the elements, all the basically nodes in our graph. and aij times this indicator vector. So let's separate these, right? I can write it aij minus aij si sj. And we had this s defined this way, right? So it means that si squared is going to be 1. So I can just plug in si squared. Let's just isolate the first term, right? And plug in si squared. And this is what we will have, right? So we knew that if we sum over all j's on aij, it is going to give us the degree, right? So we can replace that by di and si squared. And we know that we can write si as delta ij sj. So we use that and we write it this way. Now we have an si and sj. So we plug this back into our original equation. And this is the relation that we're left with. So we have sij here, we factor that out, we will have di sij minus aij. And what is that? That is our Laplacian matrix, right? So that's our Laplacian matrix. We have the index notation for the Laplacian matrix. And we can write it as this form. In matrix format, we can represent our cut size for a two-class partitioning as basically this formulation. And here we see that this cut size is looking at S, which is our partitioning, and looking at L, which is the structure of the graph that we are in, right? So we can redefine minimizing of this cut set as in terms of the Laplacian, right? So we can, so that's basically where why we wanted to introduce Laplacian, to reformulate our basically problem in terms of the Laplacian matrix. Now, let's look at ratio cut, and let's see how we can partition, basically reformulate this in terms of this relation. So let's consider a vector Si, where it is defined in this way. I actually forgot to fix this. There's a, so it is A bar over A, and this is A over A bar. So for vectors, basically for nodes that are a member, basically a member of cluster 1, we assign this positive square root of A bar over A. And for basically the ones that are a member of the complement of that, you're assigning A over A bar square root times -1. Okay, so from properties of our Laplacian matrix, we remember that for any vector, essentially, we can write the quadrant, basically this form, STLS, as basically in this term in index notation as Aij times Si minus Sj squared. And so now we have that, and we can, write it in terms of different clusters, right? Because we have plugged in our S. So what that means is that if these two belong to the same cluster, right? So if they belong to the same cluster, what is this going to be? Si minus Sj is going to be 0, right? So I'm sorry, it's not going to be 0. It is going to be basically non-zero. It is going to be yeah, it is non-zero. So this is going to be what it's. If they are basically a member of the same thing, it is going to be 0, because if you're saying same thing minus itself, it's going to be 0. Yeah, sorry about that. So so we can basically rewrite this sum in terms of looking at the nodes at different clusters, and then we plug in values here. And because it is sum, basically squared, it doesn't matter which one we're plugging in, because at the end of the day, it is going to be the same value. And then we're saying that this whole term does not have any I and j indices. So I can take it out of this summation and bring it out. And I just say what I basically write it down. A bar over a square, basically square root square. This square root is going to go away. This square root again is going to go away. And each one of basically sum of these two time each other two times these two time each other. These are going to cancel out. These are going to cancel out. It is 2 that is left. Okay, so we wrote STLS in this term, right, in this form, and then we can separate 2 into 2 ones. So 2 is equal to 1 plus 1, and we can write each of those as one of them as A over A, the other one as A bar over A bar, and that's what we're gonna write it as. And then we are saying that these two have the same denominator and these two have the same denominator. This is what we are left with, okay? And now these are the same things, right? And both of them are, so what's the sum of the nodes in cluster 1 plus the nodes, size of the nodes in cluster B is gonna be the total number of nodes that we have in graph. So it is gonna be the size of set of nodes in the graph. And this is 1 over A bar. So far, everyone follows. So this is 1 over A, this is 1 over A bar, and we have 2 clusters. So we can add a sum over different clusters and write that as AK in the denominator here. And this is gonna give us the formulation for the ratio cut, right? Which was the total number of the edges that cross boundaries of clusters divided by the size of that cluster. That basically is the definition. So this is the definition, 1/2, sum over clusters, sum over nodes in cluster 1, sum over nodes in cluster 2. This is the definition for our ratio cut. And we wrote this STLS as V times basically our ratio cut. And so we can reformulate ratio cut in terms of Laplacian equation, a Laplacian matrix of the graph. So there are two properties. There are two properties that our vector S element basically should have. One is that if we sum over all the elements in that vector S, it is going to be 0. So if we look at what we defined, we see that we can write this as sum over all elements of SA, which is sum over all elements SA that are in cluster 1, plus sum over all elements that are cluster 2. And we can write it in this manner, right? So this doesn't have any indices I, it comes out of the sum, same for this guy, and it is just sum over all elements, sum over all elements of 1 basically cluster. So it is just 1 times the size of that cluster, which is size of that cluster, right? So this cancels out with this A. It's gonna basically have the square root of A bar minus the square root of A bar. It's gonna give us a 0. And since all the elements of this are essentially the sum over all elements of SI is 0, it means that it is perpendicular to the vector of 1s. So that's one constraint for our optimization problem. The other constraint is that if we find the square of its L2 norm, it is going to be equal to the total number of the nodes. So the size of that S, vector S, is basically square root of the total number of the nodes that we have. And we can show that again, like we showed before. We write this as basically sum over all the squares of all the elements. So this way, And then again, we can take these like we did before out of the summations, and that's going to be only sum over ones for all the nodes. So it's going to be the size of that cluster, same again, size of the other cluster. And this is just gonna, everything is gonna, I think I forgot there should be a bar over here. So these are gonna cancel out. It is just gonna be sum of these two, which is gonna be V. So we can rewrite our ratio cut as this optimization problem. V, the size of the nodes of total, basically nodes in graph, is just some constant. I can remove that from our minimization problem. So STLS subjected to S being perpendicular to 1, and then the size of that vector being square root of the total number of nodes that we have. So I think let's keep this last one for the next session. Okay, just let's go over some summary. We looked at general problem of graph partitioning today, and we started by defining what cut set means. Then we used this definition of the cut set. We basically said what edge cut set is, node cut set, and we used this whole definition of cut set to define our partitioning problem. And for this partitioning problem, we said that we can't just minimize our cut size. We need to do some normalization. We defined two types of normalization. One was called normalized cut. The other one was called ratio cut. Then we introduced our graph Laplacian, and we use that graph Laplacian. Basically, we define graph Laplacian and its properties and the intuition behind why we call it such. And then we used this graph Laplacian to reformulate our graph partitioning problem into a minimization, optimization problem in terms of that Laplacian matrix, which then we call it a spectral partitioning. And then these two items are left for the next session. Okay, that's it for today. I will see you guys next time.